everyone. This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. So welcome to this lecture. In this lecture, we'll discuss about error detection and correction codes. What do you mean by error detection? What do you mean by error correction? Where actually it is used will be, and what are the various types of error detection and correction codes we have, and how to detect the errors. If the error is detected, how to correct the errors, we'll be discussing in this lecture. So error detection and correction codes plays an important role in the transmission of data from one source to the another source. So means we always transmit the data from source to the destination. So due to the noise, whatever the information that was transmitted may not reach the destination properly. So that means due to the external disturbances, the information get deviated. So in order to send the error-free, in order to have error-free transmission, we are going for this error detection and correction codes. So that means we will be generating some codes such that it will be decoded at the receiver. The code will be generated at the transmitter side and it will be decoded at the receiver side such that errors will be avoided. Okay, so the noise also get added into data when it transmits from one system to another system, which causes errors in the received binary data at the other side, that is at the receiver side. So the bits of data may change from either 0 to 1 or 1 to 0 due to the interference of noise while transmitting. So for example, what does it mean? For example, I want to actually transmit this data. This is my data at the transmission side, okay, at the transmitter side. But after sending it through the channel, the receiver has received a message like this. So here the bits got changed. This bit is 1, but actually at the receiver side, it got changed to 1. It got changed to 0. And similarly, this bit is 0 at the transmitter side, whereas it has received as 1 at the receiver side. So, but the receiver will not know whether the information received is correct or not. So, until unless we use any other mechanism for detection, so then only the receiver can identify whether the message received is correct or not. So, but actually here there is an error. Okay, there is 2 bits of error here. But without any codes, the receiver cannot identify the errors and the receiver will consider the message received is the correct only. So that leads to some improper communication. So that is why in order to avoid all this, so what happened here? This bit got changed from 1 to 0 and this bit got changed from 0 to 1. So that means due to the noise or external disturbances, the data may change from either 1 to 0 or 0 to 1, which leads to some errors in the transmission. Okay, so for avoiding for that, we are going for error detection and correction codes. So it is impossible to avoid the interference of noise, but it is possible to get back to the original data. So we cannot avoid the interference of noise during the transmission. But what is the other way? What is the other possibility? That instead of avoiding the interference of noise, we can retrieve the original data after the transmission. For this purpose, first we need to detect either an error. First we need to detect an error. Either Z is present or not using the error detection codes. So that means first we need to identify whether an error has occurred in the message or not. For that we will be using some codes which are called as error detection codes. Once the error is detected, that means once we have identified that there is an error present in the message received, then we need to correct them. So the correction of an error can be done with the help of error correction codes. Okay, so here the error detection codes or the codes used for detecting the errors in the received data or bit stream. And in these codes, some of the bits are included or appended to the original data. So how we are going to detect the error? So we are going to add some extra bits or a stream of bits to the message or its data so that the error can be detected easily. So the error detecting codes encode the message before sending it over the noisy channels. So that means by adding some of the extra bits, we are just encoding the message into some other format before sending it through the channel. This encoding scheme is performed in such a way that the decoder at the receiver side can also find the errors easily in the received data with the higher chance of success. So that means it should be known to both the transmitter and receiver that what is the information that the transmitter and receiver has to be aware of, how many extra bits we are adding and where it is added and how it is added, what is the mechanism we are using, that should be known so that the error can also be detected at the receiver side easily if it is known in before. Okay, so that is adding extra bits to the data bits is to generate the code which is called as error detection code. Okay, so here we have basically the basic type of error detection code is parity code. Okay, so what we are doing here, we are adding extra bits to the message bits. Okay, how we are adding extra bits? So the parity code is the basic error detection code in which we will add one parity bit either to the right of the LSB or to the left of the MSB. That means we will add an extra bit. That extra bit may be either added to the least significant side or to the most significant side. If you are adding extra bit to the LSB, then it should be added to the right side of LSB. And if the extra bit is to be added to the MSB, it should be added to the left side of MSB. Okay, so this is the parity code in which an extra bit is added to either the right side of LSB or to the left of MSB to the original bit stream. And the code generated is called as parity code. On the basis of the type of parity being chosen, we have two types of parity codes. Those are even parity and odd parity. How we can define the even parity and odd parity? If an extra bit is added such that the number of ones in the code becomes even, then the type of parity is called as even parity. Next, if an extra bit is added such that the number of ones in the code becomes odd, then the type of parity is known as odd parity. So here we are going to add the extra bit to either to the LSB or MSB such that the number of ones in the code becomes either even or odd. Depending on the number of ones in the code, we can have different two types of parity codes, that is even parity code and odd parity code. For example, even parity code. So for example, we have a message here. We have our data which is 11101. This is my 5-bit data. Okay, so I'm going to add. So this is my 5-bit data. 1, 2, 3, 4, 5, 6. So I'm going to add an extra bit to the left side of MSB. This is my MSB and this is my LSB. I'm adding my extra bit to the LSB side. So here my message is 11101, right? So here I have to choose the parity bit such that in order to have even parity, then what should we have? We should add an extra bit such that the number of ones in the message will become, or else the entire code becomes even. So already how many ones we have? 1, 2, 3, 4. Already even number of ones we have. If I add one more one, it becomes odd. So I need to take this bit as 0 so that the number of ones becomes even. So this is how the message can be added. So for example, let us take another message which is 11001. This is my message. Now I want to generate a code by using even parity again. So what should we do? Again, I'm adding the bit at the most significant side. So 1 0 0 1 1. This is my parity bit. Okay. So how many ones we have in the message? 1 1 1 2 3 3. So in order to make even parity, the parity bit or else the extra bit added should be equal to 1 such that the number of ones becomes in this one. Number of ones in the entire code becomes 4, which is even. So that means, I hope it is clear. So depending on the number of ones in the message, we need to take the value of parity bit as either 0 or 1. So this such that the number of ones in the entire code becomes even. So in the above example, as already we have 4 ones here. So as it is even parity, so we have taken the parity bit as 0. Whereas in the second example, the number of ones are in the message are 3. So in order to have even number of ones, so we have chosen the parity bit as 1. So that means depending on the parity, type of parity required, we need to select the parity bit as either 0 or 1. That is about even parity. Now coming to the odd parity. So as I already told you that the value of our odd parity bit should be 0 if odd number of ones present in the binary code. Otherwise, it should be 1. So that means odd parity. How can we define the odd parity? An extra bit added to the message bit such that the number of ones in the code becomes odd. Okay. So if the number of ones in the message already is odd, then the parity bit should be taken as 0. If it is even, in order to make it odd, the parity bit should be taken as 1. So for example, we will take the same data 1 1 0 1 1 0 1. This is my message or else data. So now I want to generate the code that is odd parity by using odd parity. I want to generate a code that is error detecting code by using odd parity. Okay. So now what should we do here? So we need to add an extra bit here again along with the message. Now I am adding to the LSB side. I'm adding an extra bit to the LSB side. So as I told you that I can add a parity bit or else an extra bit to either LSB side or MSB side. If I'm adding a parity bit on the LSB side, then it should be added to the right of LSB. This is my LSB, right? This is my LSB. So 1 0 1 1 1. This is my MSB. So here now I want to have odd parity. Already the number of ones are even. So I have to choose the parity bit as 1. So what is the code we have generated? 1 1 1 0 1 1 with odd parity. With odd parity. So that means whenever you are transmitting the message, as you have added parity at the LSB side, this information must be known to the receiver also. And what type of parity you are using and which position you are adding the parity bit. That must be known to the receiver so that he can easily decode the original message. So this is odd parity. For example, next let us take 1 1 0 0 1. So this is my message. So now again I am adding extra parity bit here. Now I am adding an extra parity bit here. So which is at the LSB side. So now again I want to use odd parity. So as already the number of ones in this code is 3. So I have to, as already odd number of ones are there. So I have to take the parity bit as 0. So this is the error detecting code with odd parity for the message 1 1 0 10. This is the code. Okay, with parity added. This is how. So now at the receiver side, as we know that the transmitter side we have used the odd parity, and the parity bit was added at the LSB side. So now at the receiver side, for example, the message received was 0011. So now this is a message received by the receiver. Now first the receiver will check how many number of ones are there in the received message. So how many number of ones? It is 4, where it is even number of ones. But actually what was the parity used at the transmitter side? It is odd parity. So as the parity is deviated, so the receiver can identify that there is an error in the received message. So can he identify in which position the error is? No, he can only detect there is an error, but he cannot detect which position he has error. Whether this may have error, or this position may have error, wherever we may have error, but it is not possible to detect the error, locate the error. Only we can detect the error as the parity has been deviated. We have identified that there is an error, but we cannot find out the location of error position. So that is a major drawback of parity. So what is that? We cannot detect the location of error. Detect the location of error position. Location of error bit. Okay, location of error bit. This is the drawback here. We can detect the error by just checking the parity at the receiver side. Whether it is matching with the transmitter side parity, then there is no error. If the parity is mismatched from the transmitter side, then we can say that there is an error. We can detect the error, but we cannot locate the position of the error. Now, one more. For example, here actually this was the message transmitted, but we have received this message. Okay, we have received this message. Instead of this, we have received this message. So, what was the parity that was used at the transmitter side? Odd parity. Now, at the receiver side, what is the number of ones? It is 3. So, what is the type of parity here? It is also odd. Okay, it is also odd. So, as a parity is matched, the receiver will think that as a parity is matched with the transmitter side, so there is no error. But actually, there are 2 error bit positions. As here, this is error and this bit is also error bit position. So, as we have 2 error bit position, even though we have 2 errors here, the parity is matched. So, the receiver will think that the message received is correct. Okay, so that means what I want to say here is this parity code is used only for detecting single bit errors. It is used only for detecting single bit errors. If there are multiple bit errors, it cannot detect because the parity will be matched here. So that is why the receiver will think that the message received is correct. But actually there are 2 error bit position, and hence even we have odd number of parity, the message received is correct. So that means what I want to say, the parity code is having 2 limitations. The 2 limitations are we cannot detect the location of the error bit position, and it is used only for detecting the single bit error. That means if you are locating the error, we can correct the error, right? So only simply changing the ones to zeros and zeros to ones. But we cannot detect the location, so we cannot correct it, and it is also used for single bit error detection. So these are the limitations. This parity code will not be used for detecting errors of more than 1 bit. Okay, so that is about parity code. So as it is having limitations, we are going for the another code, which is Hamming code, which is a error detection and correction code. Which is error detection and correction code. Error detection and correction code. So here, Hamming code was developed by the scientist named Hamming. So, and hence it has come after his name. Hamming code is useful for both detection and correction of error present in the received data. This code uses multiple parity bits. Whereas in the parity code, we were adding only one extra bit. Whereas in this one, we'll be adding multiple parity bits here. And how many number of parity bits are to be added will be decided by this criteria. That is 2 power k less than, greater than or equal to n plus k plus 1. What is n here? N is the number of bits in the binary code, or else we can also call it as data or message. Data or message. Okay. And k is the number of parity bits that are to be added. And hence, finally, the Hamming code length will be, so what actually we have n bits in the message and we are adding k bits of parity. So finally the code length, Hamming code length will be equal to n plus k. So that is, the criteria should be satisfied. That is 2 power k greater than or equal to n plus k plus 1 in order to decide the number of parity bits to be added. Number of parity bits to be added. And we are deciding the number of parity bits to be added based on this criteria. And where to add these parity bits? So the parity bits are to be added in the positions of powers of 2. So we'll have a position for each and every bit, right? So every position which is mentioned as a power of 2, which can be represented as a power of 2, there we can place a parity bit. So that means this code uses multiple parity bits which are to be added in the positions of powers of 2, and the number of parity bits to be added is decided by the criteria or else principle, which is 2 power k greater than or equal to n plus k plus 1. Okay, so once it is decided, now how to get the values of parity bits? Now we are locating the parity bits, and what should be the parity bit value? So again we need to identify, we have two types of parity, that is even parity and odd parity. So the group of parity bits are again added such that the number of bits can be, a number of ones in the code can be either even or odd. Okay, so now how to get the values of parity bits P1? So find the values of P1, value of P1 based on the number of ones present in the bit positions B3, B5, B7 and so on. All these positions, all these bit position suffixes in their equivalent binary have ones in the place of 2 power 0. So that means as parity bit P1 is placed in 2 power 0. Okay, so that is first place. So here we need to check for all the combinations where all the bit designations have the binary value 1 or else the value 1 in its 2 power 0th position. So these are the positions here. So we need to check these bit position values B3, B5, B7 and so that the parity can be decided based on the type of parity, either it is even or odd. And parity bit P2. Parity bit P2 can be, value can be decided by considering the bit position values B3, B6, B7. Why? Because P2 is placed in 2 power 1. 2 power 1, it is 2. What is the binary equivalent of 2? 0, 1, 0. So now we need to check for all the positions which have its second bit as 1. So what are all the positions which have second bit as 1? For example, 0, 1, 1, whose second bit is 1. Next 1, 1, 0, whose second bit is 1. And 1, 1, whose second bit is 1. Whatever it may be the other bit position values. So it is 3, 6 and 7. So that is why in order to find out the value of P2, we need to check the bit position values 3, 6, 7 and again based on the parity, this P2 value can be assigned. And similarly P3, where P3 is placed in the next powers of 2 position. What is the next powers of 2 position? 2 power 2. What is it? It is 4. What is the binary equivalent of 4? 1, 0, 0. MSB is 0. So MSB is 1. So now check for all the other combinations. What are those? 4, next 5, next 6, 1, 1, 0, 1, 1. That is 5, 6, 7 are the bit positions which are having and its MSB as 1. So that is why in order to evaluate P3, just check the combination bit position values 5, 6, 7 and place the value of parity such that the number of ones in this bit positions may be either even or odd. Okay, so similarly, we can also find the values of any other parity bits added. Okay, so we need to identify the location of parity bits and get its binary equivalent. And in that binary equivalent, consider the positions where it has 1 and check for all the other bit positions in which that corresponding position is 1 and take the value of parity bit such that it is either 1 or 0 such that it is satisfying the even parity or odd parity. So I hope it is clear. Even if not, we will be discussing a problem so that you can understand easily. Okay, once it is done, we can generate the parity code. Okay, so now first of all, we will generate the Hamming code. After that, so you remember, Hamming code will be generated at the transmitter side and detected, that means error will be detected at the receiver side. So now I have given you the procedure for generating the Hamming code. Once the Hamming code is generated, we will be going for the receiver side, how to detect the Hamming code, how to detect the error and in which position we have an error. So first of all, let us find the Hamming code for a binary code D4, D3, D2, D1 whose value is 100. Consider even parity. The number of bits in the given binary code is 4. So here I have a 4-bit message which is to be transmitted. So I want to generate a Hamming code for this 4-bit binary code here. So now for that, first of all, let us try to find out, let us consider step 1. What is the step 1? We need to identify the number of parity bits to be added. Number of parity bits to be added. So how can we identify the number of parity bits to be added? Based on the criteria 2 power k greater than or equals to n plus k plus 1. So what is n here? Number of bits in the message. What is n here? That is 4. N is equals to 4. Now if I take k is equals to, it is a trial and error method. If I take k is equals to 0, 2 power 0, is it greater than or equals to 4 plus 0 plus 1? So what is this side? 5. Is 1 is greater than 5? No. So k is equals to 0 is not. K is equals to 1. So how much? 2. 2 power 1 which is 2, which is 4 plus 1 plus 1. So how much we have here on the right hand side? It is 6. On the left hand side it is 2. Is it satisfied? No. Now again k is equals to 2. So it is 2 power 2. This is 4 plus 2 plus 1. On the right hand side it is 7 and on the left hand side it is 4. Is 4 greater than 7? No. So this is not satisfied again. Now let us take k is equals to 3. So if I take k is equals to 3, 2 power 3, 4 is the message bits, k is a parity bits plus 1. So what is this one? 8. And what is the left hand side? It is also 8. So it is equal to 8. So this condition is satisfied. So now we have identified the number of parity bits to be added is equal to 3. So that is k is equals to 3. Now what is the length of the Hamming code? Length of the Hamming code is equals to n plus k, which is 4 plus 3, which is equals to 7. Which is equals to 7. 7 is the resulting Hamming code length. So here, now step 2. Now step 2, locate the parity bits. Locate the parity bits in the powers of 2 position. In the powers of 2 position. Okay, first of all, how many bit code it is? Resulting Hamming code will have 7 bits. 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6 and 7. Okay, so is 1 can be represented as a power of 2? Yes. This 2 can be represented as a power of 2? Yes, it is represented as 2 power 1. Is 3 can be represented as a power of 2? No. 4 can be represented as a power of 2. Any other things that can be represented as power of 2? No. So, these positions we need to place the parity bits P1, P2, P3. And the remaining bits should be placed with data bits. What is a data bit? D1, D2, D3, D4. That means D4, D3, D2, D1 are occupying the positions 3, 7, 6, 5, 3 respectively. Whereas in the position 1, 2, 4, we are keeping the parity bits. So this is our resulting Hamming code. Now, as we all know these values, D1 is what? What is a code given? 0, 0, 0, 1. We need to find out the values of these parity bits. We have to find out the values of these parity bits. So for that, I am constructing a table here. I am constructing a table. So wherein first column is bit positions. Okay, bit positions. So what are the bit positions here? 7, 6, 5, 4, 3, 2, 1. So these are the bit positions. Okay, and then bit designations. Bit designation means what? So this bit is P1 is represented as 1 is represented as parity bit 1, parity bit 2, whereas fourth position is represented as parity bit 3, and this is D1, D2, D3, D4. And then we are going to write binary positions. Binary positions. Okay, so the next column, next row is binary positions. So what I'm doing, I'm writing the binary values of the positions. So how can I write the 7? I can write 7 in binary as 111, 6 as 110, 5 101, 4 100, 3 011, 2 010, 1 001. Right? Now, these are message bits, or else we can also write it as data bits. So what are the message bits? 1 0 0 0. And now we need to find out the values of parity bits. We need to find out the values of parity bits. So here these are the parity bit values. So now we need to find out the parity bit values. So for that, first parity bit P1. In which position it is? It is in the first position. It is in the first position. What is the binary equivalent of this first position? 0 0 1. Now check for all the combination, all the other positions which have received its LSB as 1. That is 3, next 5, 7. So 3, 5, 7. What are the values of this? 3, 5, 7. So 3 is, this 3 position is 0. And 5 is 0 and 7 is 1. Now, how many ones we have? So, in the problem it is given that we need to consider even parity. Even parity. So, how many ones are present in these 3 positions? Only 1. It is odd. So, as it is odd, in order to make it even, I should take P1 as 1. In order to maintain even parity, among these positions, we have only 1 which is odd. In order to make it even, I am taking P1 as 1. Now let us take P2. What is the P2 position? It is second position. What is the binary equivalent of this second position? 0 1 0. So it has received its second bit as 1. Now check for all the other positions which have its second bit as 1. So it is 3 again, and next 6 7. So 3 6 7. What is the value in the third position? Third position it is 0, 6 it is 0, and 7 it is 1. Again, how many ones we have? 1, which is odd again. So again P2 must be taken as 1 in order to make it even. Now coming to P3. So it is in the fourth position. What is the binary equivalent of fourth position? 1, 0, 0. So it has received MSB as 1. Now check for all the other combination other than P3 which have its MSB as 1. Whatever it may be the other position, other bits. If it is having MSB as 1, just consider it. So 5, 6, 7 is also having its MSB as 1. So what are the values of 5, 6, 7? 5 is 0, 6 is 0, 7 is 1. Again it is odd parity. So in order to make it even, again P3 also must be taken as 1. So that is P3 is 1 and next P2 is also 1, P1 is also 1. Now our Hamming code. What is our Hamming code? Hamming code is of having length 7 in which we have D4, D3, D2, next P3, D1, P2, P1. So D4, D3, D2, 1, 0, 0. P3 is 1. D1 is 0. P2 is 1. This one is 1. So this is our resulting Hamming code such that even parity is maintained. This is our Hamming code. So that means before transmitting, we will be adding parity bits, that is group of parity bits, which will be decided based on the criteria 2 power k greater than or equals to k plus n plus 1. Okay, after adding this, we will be sending this through the channel. So at the receiver side, the receiver will decode this Hamming code and he will be able to find out whether it is having any error. If it is having error, then in which position we have an error. That can be identified at the receiver side. So this is about the generation of Hamming code. Okay, now let us see how to decode the Hamming code at the receiver side. So here, now we will be finding out the check bits which will decide whether there is an error or not. If there is an error, in which position we have an error. In order to find it out, we'll be finding the check bits. So in order to find out the check bits also, we again need to construct a table like this and we need to check for the parity of each and every parity bit. Okay, if the parity is matched, then the check bit will be considered as, that means each and every parity bit will have a check bit. If the parity is matched with the transmitter parity, then the check bit is considered to be 0. If the parity is not matched, then the check bit is considered to be 1. So again, how to calculate, how to generate the check bits? Again, as I said you that for each and every parity bit, we'll have a check bit. So here, find the value of check bit C1 based on the number of, this check bit C1 is for parity bit P1, which is placed in the position that is first bit position, right? So now in order to generate this check bit, we need to go for P1, where P1 whose binary equivalent is 001. That means we need to check for the combination which have received LSB as 1, including parity. Whereas in case of generation of Hamming code, we have excluded the parity bit. Now in this case, we need to include the parity. So including parity, 1, 3, 5, 7 positions has received LSB as 1. Now check all these 4 bit positions and whether these 4 bit positions are matching the parity with the transmitter side parity or not. Okay, if the parity is matched, then C1 should be taken as 0. If the parity is not matched, this is matched, it is a matched condition. If it is not matched, then the parity check bit will be considered as 1. This is in case of mismatch. Similarly, parity bit P2, which is placed in the position of 2 power 1. Okay, 2 power 1 means it is 2 whose binary equivalent is 0, 1. 0, 1, 0. So that means whose second bit is 1. So we have the positions which have its second bit as 1, that is 2, 3, 6, 7. So check these bit positions. If these bit positions are having number of ones which are matching with the parity at the transmitter side, then C2 will be considered as 0. If it is not matched, then the C2 will be considered as 1. Similarly, C3, this is for P3, which is placed in the position of 2 power 2, which is 4, whose binary equivalent is 100. Now check for the combination bit positions which have received its MSB as 1, that is 4, 5, 6, 7. So now again check the number of ones present in this combination. If it is matching with the transmitter parity, then C3 will be considered as 0. If it is not matched, then C3 will be considered as 1. Then after finding out this C3, C2, C1, then we need to form a syndrome. So how to form a syndrome? Syndrome is nothing but we placing the check bits in the order C3, C2, C1. This is nothing but our syndrome. So this syndrome will decide the position, error position. In which position the decimal equivalent of this syndrome will decide the error bit position. Okay, so after finding out the check bits, just form a syndrome in the order C3, C2, C1. Then the decimal equivalent of this syndrome will give you the error bit position. Okay, if the syndrome decimal equivalent is 3, it indicates that third position is having error. Okay, then we can correct them. After after finding the location, just we can remove the parity bits and we can extract the error bits here. So because we already know that as we are using Hamming code, the receiver will also know that the number of parity bits are added is based on the criteria, that is 2 power k greater than or equals to n plus k plus 1. So he will be deciding the number of parity bits added based on the length of the code. After deciding the parity bits added, he will be eliminating the parity bits and he will be extracting the data bits so that the original message can be recovered at the receiver side. So now we'll take this problem. So actually the message transmitted is 1001011. This is the transmitted message. So now what I'm doing is I just wanted to show you whether it detects the error properly or not. So I'm changing this bit. What is this bit position? 1, 2, 3, 4. Fourth bit position as I'm changing it as 0. So 1000011. So this is my code transmitted. That means this is the received message. Instead of this message, the receiver has received this message. As we know that this position is having error, but the receiver has to decode whether this position is having error based on the Hamming code. So now I'm writing a problem here. The message received is 14011. So the message received is 14011. Detect whether there is an error. Detect whether there is an error or not in the received message. In the message, and also find the location of the error. Location of the error and retrieve the original message. Retrieve the original message. Okay, so this is the kind of problem given. So now coming to the solution. So here we have Hamming code. We have, or else received code also we can write. Hamming code is 14011. So what is the length of this one? Length of this code is 7. Length of this code is 7. So as the length of this code is 7, so we can identify that we can identify that the number of parity bits added is equals to k is equals to 3. That means we have 3, or else we can also write down the location here. We can also write down the designation. So how many bit code it is? This is 1, 2, 3, 4, 5, 6 and this is 7, right? So now we'll write this 0, 0, 0, 1, 1. As at the transmitter side, we have used Hamming code. We can identify that all the powers of 2 position, which is 2 power 0, 2 power 1, 2 power 2, will have parity bits P2, P3 and the remaining are the message bits. This is D1, D2, D3, D4. That means K is equals to 3 we can identify and N is equals to 4 because as we have used a parity Hamming code in all the powers of 2 positions, we'll be having parity bits. So how many parity bits position, how many parity bits we have? 3 parity bits here we have P1, P2, P3. So now we are going to find out whether there is an error or not. For that, we will be constructing a table. So, we'll be constructing a table again here. So, bit designation, okay, and then bit value, and then binary positions. Binary position. Only we'll have 3 rows here. Okay. Only we will have 3 rows. 1, 2, 3, 4, 5, 6, 7. Okay. 7, 6, 5, 4, 3, 2, 1. So it is we have the value 1, 0, 0, 0, 0, 1, 1. So what are the designation? Bit designation. Bit designation I didn't write. Okay. Bit designation. Actually, this has to come up and this has to come down. This bit designation. So it is. So as we already know that these are parity bits P1, P2, D1. This is P3, D2, D3, D4, right? And now coming to the positions here, 1, 1, 1. This is a binary position, 1, 1, 0, 1, 0, 1. Next 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, right? So now I want to write down the check bits here. Check bit is C1 is for P1. So for P1, so what is this binary position? Binary position is 0, 0, 1. We need to check for all the other combinations which have its LSB as 1. So that is 1, 3, 5, 7. Now write down the values here from 1, 3, 5, 7. 1 is 1, 3 is 0, 5 is 0, 7 is 1. So we need to maintain, actually it is to be mentioned here, even parity. Consider even parity. Consider even parity. So now I am considering the even parity here. Now, so how many number of ones here we have? Even number of ones. So if the parity is matched, then what should we do? We should take C1 as 0. If the parity is not matched, we should take the check bit as 1. Now C2, which is the C2 is check bit for the parity bit P2, which has received a second bit as 1. So for that, we need to consider the position 2, 3, 6, 7. 2, 3, 6, 7. Values of 2, 3. 1, 0, 6, 7 is 0, 1. Again, it is even parity, even number of ones we have here. So C2 also considered to be 0. Now C3, which is P3 here, where C3 is a check bit generated for the parity bit P3, for which we need to consider all the combinations which have MSB as 1, 4, 5, 6, 7. So now consider the values of 4, 5, 6, 7, 0, 0, 0, 1. So what is the number of ones here? It is 1. It is odd. So that is why the check bit should be considered as 1. Now form the syndrome. With the parity check bit C3, C2, C1, which is taken as 1, 0, 0, What is the decimal equivalent of this one? 4. That means here it decides that bit position 4 is having error. 4 is having error. So, how can we have detected the position 4 is having error. Now, how can we correct it? As it is having only binary ones and zeros, if it is 0 in the received message, just change it to 1. Okay, so the received message is received message, or else received code is 1000011. As the 4th bit position is having error, now the corrected message or else corrected code is 1001011, because as a 4th bit position is having error, so we have just changed it from 0 to 1. Okay, now we need to retrieve the original data or else original data transmitted. So by excluding the parity bits, what are the parity bits we have? P1, P2, and this is also a parity bit. So what, excluding this, we have the message bits. So this is D3, D2, D4, D3, D2, D1. So that is 1000. This is my original message transmitted. So that is how at the receiver side, the receiver can decode the message and he can identify the errors and error location, and he can also find out the corrected message, and he can retrieve the original data transmitted. So, but here also we have a limitation that we can detect only single bit error, and we can also detect and correct single bit errors using Hamming code. We cannot detect multiple bit errors, and we cannot correct the multiple bit errors using Hamming code. So that is about error detection and correction codes. I hope it is clear to you all. So parity code and Hamming code are the error detection and correction codes. So the parity code is used for detecting only a single bit error, but we cannot even correct the single bit error using parity. Where we can correct and detect single bit error using Hamming code. So I have discussed how to generate a Hamming code and how to decode the Hamming code to retrieve the original data at the receiver side. So that's all for this lecture. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.